In this video, I will talk about our project on video-based question answering. Starting with the motivation. So we are familiar with the concept of visual question answering and the VQA dataset, which deals with the ability to recognize objects. Another important attribute of humans is the ability to reason about behaviors. In our work, we try to explore this direction by using videos. On the left is a video of the game of rugby. Looking at this, we can answer some reasoning questions of the nature: who did this, what happens next, and so on. Previous work in this area includes visual question answering and also video captioning. However, in our work, we have taken a slightly different approach. We took inspiration from this paper called Neurosymbolic Concept Learner. This paper is for question answering from images. The way it works is, first, there's a detection stage where we get the location of all objects in the frame. We learn an embedding of these objects. The embedding is queried through symbolic queries like shape of, color of, etc., which maps into a concept embedding space. A similarity is then computed between the current projection in the space and other available embeddings of concepts to get the answer. This embedding space is also learned during training. Since the questions we are dealing with in our project are somewhat complex, we thought of using the symbolic logic method for question parsing. The dataset we are considering is CLEVRER, which consists of videos, questions, and answers. The questions are of four major types: descriptive, explanatory, predictive, and counterfactual, all requiring a high-level understanding of the video. Here is the overview of the method we propose. It consists of two major branches. The top one is for parsing questions, and the bottom one is for the video. Using a bidirectional GRU, we convert the natural language questions into latent programs. As we can see, these programs are hierarchical in nature. This branch is trained using reinforced algorithm with sparse rewards. In the perception branch, we start by obtaining bounding boxes of all objects present in a frame. The box and the frame is then embedded into a latent space, and we get one embedding for each object. When we have the combined embedding for all objects in a frame, we pass it through three LSTM layers. The LSTM helps process the sequential data of the video frames and provides a compact embedding. Finally, a program executor takes the perception embedding and executes the latent symbolic program on it, which gives us the answer to the question. The perception module is trained using KL divergence between the original answer and the predicted probability distribution. For effective training, we employ curriculum learning and start with simpler questions and gradually increase the complexity. Looking at the results, we see that the accuracy is about 57% for exist type questions, but low overall. We check the utility of the LSTM layers using an ablation study where we answer questions based on a single frame. We see there is some improvement in performance for exist type questions, but no significant impact overall. Hence, we conclude that the simple LSTM layers fail to capture the complexity of information from the video. To summarize, we have introduced a framework for question answering using videos. We employed a neurosymbolic method for this. We used a combination of supervised and unsupervised method for training this. We employed curriculum learning for stable training. However, our result failed to achieve a good level of accuracy. Future work in this direction could be to experiment with more complex models for combining information from frames of a video. Also, introducing a dynamics model can help improve accuracy, especially for counterfactual questions. That's our presentation. Thank you for listening.